Hey guys, welcome back. In this lecture, we are going to talk about how we can solve problems that ask for maximum flow in the network. And a very famous and well known algorithm to solve such problems is Ford-Fulkerson. But before starting with Ford-Fulkerson, let's talk about max flow. Max flow, as the name suggests, is defined as the maximum amount of flow that the network can allow to flow from source to sink. So the prompt is we're given this graph, this network flow graph or this flow network, and we have to maximize the flow through this graph or in this network from source to sink. So we're gonna go step by step, but there are a few basic observations to be made. See this graph? Here, to go from source to sink, or we can say from S to T, there are paths. One of them is S to A to B, and B to T, right? So if you're passing the fluid through this path, how much will we be able to transfer? We can pass 3 units of water or 3 units of any XYZ fluid from S to A, right? But we can only take 2 units further to the next pipe, which is AB, because the capacity of this edge AB is 2. And then there comes the third edge, which is BT, having capacity 3. But again, as we will be having only 2 units coming from AB, we would only be able to pass 2 units from this edge BT as well. So the thing is, the amount of fluid, or you can term it flow, in this path or in any path from source to sink is limited by the bottleneck capacity of that path. Here in this path that we discussed, that we have taken from source to sink, the bottleneck capacity is 2. So we cannot transfer more than that through this path. So this was the first path that we selected. If we are selecting this path, that means we are passing 2 units of water through this path towards the sink T. So now we're gonna write this flow across the respective edge along with the capacity. So if you see this edge SA, the capacity of this edge is 3, and the flow across it, the current flow across it is 2. So there's still 1 unit of water that can be sent through this edge SA. And this remaining amount, or this remaining space for 1 unit, we term it as residual capacity. So residual capacity for SA is 1, and for this edge AB is 0, as the current flow is 2 and the capacity of this edge AB is also 2. And now this edge BT, the capacity is 3 and the flow is 2, so it can allow 1 more unit of water through it. So this was one path. We can choose more. There's another path right here. It is S to C, C to D, and D to T. Again, the minimum capacity of this path, or what we call the bottleneck capacity, is 2. So this path can also take 2 units of water to the sink. So we chose 2 paths, S to A to B, B to T, and the second one, S to C, C to D, and D to D. So we are getting 2 units to sink through the first path and 2 more units through the second path. That makes a total of 4 units to the sink. But is this the maximum that we can get to the sink? Yes, this is the maximum flow that we can achieve in this network. So this looks quite straight, right? But just wait for a minute. Let's reset this graph back to the original network where we don't have any flow going through any of the edges. Now let's say we pick this path. Or let's say our algorithm finds this path first and traverses it first. So from source to C, C to A to B, and then B to sink. I can pick this one, right? Because this is a valid path too. So if I go like this, the bottleneck capacity for this path we find is 2. So let's pass 2 units from this path. So this path leaded 2 units from source to sink. Now let's find more paths. So to increase the flow we are getting at the sink, right? So is there any path? What if we try to go like this? From S to A to B, and then B to T. So see here, this edge AB is already filled up to its capacity. So if we try to push water from S to A, then we won't be able to carry it forward to the next edge. So we will be blocked right at this edge, right at this vertex A. Now, if we try to find some other path, which can only be possible if we go from S to C. But again, see this edge S to C. The capacity of this edge is 2 and the current flow is also 2. There's no space left for more water. So we can't push more water from source to C. Again, we're blocked here. So if we first pick this path, S to C, C to A to B, and B to T, the max flow, should not term it max flow, the flow that we are getting in this network from source to sink is 2. But this is not the max possible flow through the network. We saw it a few minutes ago that the max possible flow through this network is 4. So finding a forward path from source to sink in this original graph may not always work. And here comes the concept of residual graphs. Ford-Fulkerson worked with residual graphs to find the paths from source to sink rather than finding paths directly in original network. But how we gonna get benefited by residual graph? You'll get in a minute. Residual graph, as its name implies, is something that has residual capacities. Okay, so to create a residual graph, there are two kinds of edges that we draw: edge with its residual capacity and edge with its shrinking capacity. So let's say this is the network whose residual graph we are going to draw here. So this network is the one we got when we were getting a max flow of 4 by selecting two paths, one from S to A to B, B to T, and the other one from S to C, C to D, D to T, right? So see this graph. To draw its residual graph, first we take all the vertices that we have in this original graph. Now let's draw the edges. Let's start with SA. See, in original graph, the flow in this edge is 2 and the capacity is 3. So this edge is capable of passing one more unit of water from S to A. So its residual capacity is 1. Now comes shrinking capacity. This edge, is having 2 units flowing through it, but this current flow can also be shrinked back till 0 if required. So this vertex A can say no to the source for this flow or for a part of this flow. It's a possibility. So if those units can add more value to some other path in network, we can undo the flow. So we can undo 2 units from A to S. Or we can say the flow can be shrunk back from 2 to 0. This is the way how we show it. 2 units back to source from A. So residual graph comes with the concept of shrinking the flow through edges, which indeed is important. Now let's take the next set of vertices, A, B. The current flow across AB, edge AB is 2 and the capacity of this edge AB is also 2. So the residual capacity or remaining capacity is 0. We have no space to increase the flow further. That's why no forward edge. We're not going to draw any forward edge. We can only undo 2 units from B to A. Now let's take next set, which is BT. Current flow across BT is 2, but capacity is 3. So remaining or residual capacity is 1, so it can pass through one more unit. And it can undo its current flow by 2. Now let's take SC. It's not having any residual capacity. It can only undo 2 units flowing through it, so only a backward edge. Next is CD. We can increase current flow by 1 and we can shrink it by 2. So forward edge with 1 and a backward edge with 2. Now this one DT, no residual capacity, but we can shrink it by 2. Now the remaining 3 edges, the capacity and residual capacity both are same for these edges. As the current is 0, current flow is 0 for all of them. So they can allow water equal to their capacities. So we're gonna draw them just like they are in the original graph. So this is the residual graph. After drawing this residual graph, now we can shift back to the greedy way where we now look for the forward paths from source to sink. It does not matter whether the edge the path is covering is one for residual capacity or for shrinking capacity, but it must contribute to make a complete forward path from source to sink. And we call this path an augmenting path. So see this residual graph. Do we have any augmenting path from source to sink? Consider only forward path. We can't include edges going backwards, okay? You'll find no forward or augmenting path from source to sink, which means the current flow through the complete network is already at max. Now let's compare it with the second case where the path we selected was S to C, C to A to B, and B to T. So let's draw the residual graph for this case as well, just to make the concepts clear. So here let's take the vertices and now let's start with SA. The capacity is 3 and currently there's no flow across this edge, so the residual capacity is also 3. And now the next edge, next set of vertices is AB, where we are having capacity equal to 2 and the residual capacity is 0 as it is already filled by 2 units of water. So we can only undo 2 units from B to A. Now BT, where there's space for one more unit of water from B to T, and we can undo 2 units from T to B. Now next is SC, where we have no space for more water, so we can only undo 2 units. Now CD, where there's no flow, currently there's no flow, so the residual capacity is equal to the capacity. And the same is true for DT, the residual capacity is 2. And now next edge, CA, see this edge, there is space for one more unit from C to A, so residual capacity is 1 and we can shrink back the flow by 2. Now the other two edges, they're not used, there's no flow across them, so let's draw them as they are. So this is the residual graph that we're getting. Now again look for the forward path, or you can say for the augmenting path. There is one from S to A to C, C to D, D to B, and B to T. This path is the proof that we're not getting the max flow at the sink yet. There are possibilities to increase the flow at sink. So as we got this path now, let's look for the bottleneck capacity. Bottleneck capacity for this path is 1. We have it with edge BT, right? So we're gonna increase the flow by 1 in this path. Now look at the original network. This is the path. In this, SA is now gonna have a flow of 1. And now comes AC. It's a backward edge, and the edge that we selected in the residual graph was meant for shrinking the current flow, right? So here we're gonna shrink the current flow by 1. So actually we're gonna eliminate 1 from the current flow. That's why now the flow through this edge will be reduced to 1 from 2. Now let's fill 1 in CD, 1 in BD, and BD as well. So with this, BD is now completely filled. So again, have a look at the updated residual graph. This is the updated residual graph. So let's see again if we still have any augmenting edge, augmenting path. So yes, we do have. It's from S to A to C, C to D, and T to T. So let's increase the flow in original network. Now see here, the 2 units that are reaching at C from source are getting distributed among CA and CD. But after we increase the flow in this path, in this augmenting path that we selected, what we're gonna get? Let's see. So SA, we're currently having flow of 1. Now it will be having a flow of 2 units. And now AC, which is a backward edge. So again, we're gonna eliminate 1 from this edge. And now CD, here again, we're gonna increase the flow by 1, and DT, where the flow, current flow will be 1. So this is the path, and this is the current flow across this path. Now see this edge SC. Here we are getting 2 units. These 2 units were previously getting distributed among CA and CD. Now CD is getting both the units. Remember I said earlier that we reduce the flow from one edge to adjust it to some other edge. That's what is happening here. If 2 units reach to C, they must leave C towards the other vertices, and that's also what the residual graph takes care of. And that is what shrinking the flow is all about. So in residual graph, no matter what the path you choose, it won't block other existing paths, because here we are having the concept of shrinking the already running flow. So now we are having 4 as the flow at the sink, which is indeed the maximum flow. So now if we create the updated residual network for this network, we won't find any augmenting path. So this was the core part of Ford-Fulkerson. Now let's see how we actually going to implement this. We are not going to move back and forth between the original network and residual network. Instead, from the beginning, we only going to stick to the residual graph. So this is the original network. Now we're going to convert it to residual graph, and it's going to be very easy, as initially there will be no flow in the network. That's why residual capacity for all the edges will be equal to the actual capacity of the edges. And again, as there's no flow in the network, we cannot undo anything, right? So the shrinking capacities will be 0 for all the edges. So this is the residual graph. This is the structure or graph with which we are going to start our implementation. And now we're gonna start from source to reach to the sink. Basically, we are going to find out the augmenting path. And for that, we're gonna need a map kind of structure. And we're gonna call it parent mapping, where we can store key values. Basically, this parent mapping is the one which is gonna help us in constructing the augmenting path. And now comes how we're gonna go over these vertices, or how we're gonna traverse this network. So we can either go with DFS or we can go with BFS. It's up to us. So here we're gonna go with BFS. So for that, we will be needing a queue. We're gonna push current vertex in this queue. And we're gonna take a visited set. It's gonna keep track of all the visited vertices while searching for the augmenting path in the network, so that we don't include the same vertex again in the path. Okay. So let's start with S. Let's add S in this queue and to the visited set as well as we're visiting it. And now from here, loop starts. Until the queue is filled, we pull items from the queue, or you can say we pull vertices from the queue one after the other, and we start finding the forward edges from that vertex in the network till we reach to the sink. Okay, so there are two things to be taken care of while selecting the edges. First is the edge must be having value greater than 0. And the second constraint is that the edge must not be already visited. So it must not be already there in the visited set. That's it. So S is having two edges that we can select. One is from S to A and the other one is from S to C. And remember, we only consider the outgoing edges, okay? So now we pull S from the queue, and at the same time we add the connected vertices from S to this queue that we just selected. So we selected A and C, so we add A and C to the queue, and also to the visited set as we are visiting them, and now to this parent mapping with along with the mapping. So this says that we came to A through S, and we do same for the other vertex, which is C. We came to C through S, that's why it is C colon S. C is the key and the value for C is S. So now we're done for S, and now we select the next vertex that we have in the queue. So next vertex that we have in the queue is A. So now we're going to look for the forward edges going outwards from this A to the other vertices having value greater than 0 and which are all not already visited. So see, there are three edges going outwards from these are AS, AC, and AB. But as S and C are already visited, and also these edges are having value 0, so we are not going to select them. But this edge AB is having a capacity 2, so we're going to select this vertex B while we pull A from the queue. And let's put B in visited set as well. And now let's put it in the parent mapping along with the mapping as we came to B through A. Now the next edge that we have in Q is C. So C is also having CA, CB, and CD, these three edges, but we can only consider this last edge CD as it's having a capacity greater than 0 and it's not already visited. A and B are already visited, so they are not in the game. So let's select D while we pull C from the queue. Let's put D in visited set and also in parent mapping. Now pull B from the queue, and while we pull B, we gonna put the vertices, the connected vertices from it. So the edges that are going outwards from B are BT and BD and BC and BA. But A is already visited, C is already visited, D is already visited. We are left with T, which is sync, and here the loop gonna stop. So while we pop B from the queue, we add sync vertex, which is T, into the queue. And here we stop and we add this mapping to parent mapping saying we came to T through B. So now this parent mapping is going to help us to construct the augmenting path. We start from sync and then we go all the way to source to find out the augmenting path. So we reached to T through B, and then we came to B through A, and we came to A through S. So this gives us the augmenting path. Now this path is from sink to source. Now we reverse it to get it from source to sink. Now the next step is to get the bottleneck capacity. The minimum capacity that this path is having is 2. So we are going to increase the flow by 2 in this path. So we are going to set 2 as the current flow for this path and also as the max flow for the complete network for now. As this is residual graph and we are increasing the flow by 2 in the path, so after increasing the flow, all the shrinking capacities of this path will now have 2 units of water that they can undo, right? And all the residual capacities will decrease by 2 as we have consumed space for 2 units. And that's how we're going to update these values. So we go over this augmenting path, and for all the forward edges, we eliminate the current flow from the residual capacity, and for all the backward edges, we add the current flow in the shrinking capacity. And that's how we get all the updated edge values, and then we repeat this complete process until there is any augmenting path present in this network. And this max capacity, this max flow, this variable gets updated each time we increase the flow in the augmenting path that we get in this process. So we keep adding up the flow for each path in max flow, and at the end this will be having the maximum flow in the network stored in it. So this is how everything is going to work.